would like to introduce our first speaker. The first paper, a study of magnesium-modified ZSM-5 catalyst physical and diffusional characterizations. The authors are W. Thomas Moe and James Way of the Massachusetts Institute of Technology. Dr. Moe will present the paper.
Thank you, Professor Zaffi, and good afternoon, ladies and gentlemen. Today I'll be talking about part of my graduate thesis work at MIT completed roughly 6 months ago. Can I have the first slide, please? The topic of the talk is a study of magnesium-modified ZSM-5 catalyst physical and diffusional characterizations. The talk will be roughly divided into 3 parts. First, the motivation of this work. The second is the physical characterization of catalyst morphology after modification. And the last one would be the measurement of its diffusional parameters and what we can learn from this study in terms of catalyst design. The motivation for modifying ZSM-5 with magnesium really centers on the idea of so-called para-selectivity. ZSM-5 is a crystalline aluminum silicate with a pore diameter around 5.5 angstroms. This is roughly the size of the alkyl aromatic hydrocarbons. And in the case of xylene isomers, the 3-xylene isomer, the para-xylene has a molecular diameter along the axis of the substitutional group about half an angstrom smaller than the other meta and ortho isomers. However, when diffusing in zeolite crystals, it is reported that the diffusivity of para-isomer is at least 3, even as high as 4 order of magnitude faster than the other 2 species. So when xylene is produced in ZSM-5 by using either alkylation of toluene or toluene disproportionation, under certain conditions, we can observe the selectivity, the product, contain as high as 97% of para-xylene. This is very high selectivity toward the conventional product you will get out of amorphous acetic acid catalyst, which may compose about 25% para-xylene in a thermodynamically equilibrated product mixture. And the separation cost is tremendous in this system, and it has a great advantage if we can have a catalyst that persistently produces high selective product. The conditions for this high selectivity to be observed are following. Either it's a high temperature or it's using larger crystals. Both indicates a diffusion limited case, or more interestingly, when you have a small crystal that is not para-selective, but you impregnate it with some inorganic solutions and calcine it. These inorganic compounds including magnesium, phosphorus, boron. And suddenly, after the calcination, you run the same reaction, you can turn very high selectivity of para-xylene. And it's explained by when you bring the overall system from reaction control condition into diffusion limited condition, that you can recover only the fast diffusing species. This is equivalent that you have a diffusional separation scheme superimposed on top of your highly acidic catalyst, which would be very advantageous. Using the conventional linear diffusion and reaction model, we can compute using conventionally reported parameters, physical chemical parameters. We can calculate the para-selectivity of para-xylene as a function of toluene conversion in toluene methanation reaction, as a function of different Thile modulus. Now, if you have a crystal that is non-selective at low Thile modulus system is reaction control, you produce mostly thermodynamically equilibrium controlled product, but somehow you can engineer the system to increase the Thile modulus. For example, impregnate it with magnesium, and you can bring up the Thile modulus into diffusion limited region, and then you can achieve very high selectivity of para-xylene even at the very substantial conversion of your toluene reactant, and it will be a very attractive alternative to design your catalyst under this principle. In order to systematically study the system, in the following part I wish to present 2 things about the system. First, I'd like to know where are these magnesium located after they're getting introduced into the system? The secondly is how much diffusivity has been retarded by the modification. In order to do this systematically, what I have introduced is a way of bracketing my system. I incorporated initially a certain amount of active hydrogen form of ZSM-5 with a given amount of magnesium acetate agent, mix them for a long time so they are equilibrated. After that, I have two ways of either I leave all the magnesium that I used initially in the system, keep them as much as possible, and calcine them, produce the sample, what I so-called surface-coated magnesium. Then this is representative of the maximum incorporation because I try my best to get everything in the system stay there. Or on the other hand, I wash out all the excess solutions and keep the part that is only equilibrium control, that is being ion exchanged with the proton of my starting material, and I calcine the system, so I produce so-called ion exchange modification. By doing this, potentially I bracket my modification range by using maximum and minimum amount for the given pair of material. So for each material I start with, I can produce a pair of samples and examine the difference of their behavior. First, I'd like to introduce some of the morphology by characterization results. These are scanning electron micrographs of starting materials to unmodified. This is the base material. It's all the same for all my studies. This is a twin of two crystals and some multicrystalline, and this is a ion exchanged sample. And from the morphology, you cannot tell any difference. They are pretty much clean on the surface. However, for the surface coated sample where I keep all the magnesium that I put in beginning in the system, you will see a sample with 3.6, 4.9, 9.8 weight% magnesium. We see more and more of these about clusters or spheres on the order about 0.1, 0.2 microns start accumulating on the surface. In this sample, if you look closely, actually, almost seemingly the whole surface is covered by the magnesium spheres. The X-ray photoelectron spectroscopy allows us to examine more closely what the surface composition is. Plotted here are samples for silica-like, which is a ZSM-5 without any aluminum active sites. And here is hydrogen-formed ZSM-5 as the base material I use in all the studies, and 3 progressively loaded magnesium modified samples and a pure magnesium oxide material. And we can see as loading increases, we have more and stronger magnesium signals on the surface. However, the interesting thing is, from the previous picture, we see almost the whole surface is covered with magnesium spheres in this highly modified sample. We never see the complete vanish of silicon signal, which indicates there is still exposed surface that is not blocked by this heavy modification and is still open to the diffusing of reactant and product in and out of the system. To examine a little bit closer, I've lifted temporarily just. This is a secondary ion mass spec study, which is the most surface sensitive tool to examine the composition. Plotted here is the magnesium to silicon, the two mass 24 against mass 28 peak ratio for a pair of samples. Remember, this is starting exactly the same material, but one of them washed out all the excess magnesium, so I have an ion exchange sample. The other one keep everything in there. So remember, the y-axis scale is completely different. However, so for the ion exchange sample, we see a pretty flat profile as a function of the argon sputtering time. The argon, under this argon gun condition, I am sputtering roughly about 1 or slightly less than 1 angstrom ideal film from the surface per minute. So what we see here is roughly the removal of the surface thickness from the modified sample. The interesting thing is here, for the modified sample, the coated sample, we're seeing a dramatic drop in the first few tenths of angstrom of sputtering. Remember in the picture, we saw the clusters or spheres of magnesium oxide. Those sizes are on the order about 0.1 micron, is about 1,000 angstroms. There's no way we have sputtered them off from the surface. So what apparently we're seeing here is a gradual removal of a invisible magnesium oxide film. There's a second morphology of magnesium oxide existing on the surface in review by the sputtering process. Now, so much for the exterior of the catalyst. What its interior looks like. Seen here is I put the sample in a resin, grind it open with diamond polish, and then I examine it under electron microprobe. Seen here is a micrograph from the electron microscope. This is the sample itself. This is the X-ray mapping of the part that emits silicon signal, which is the core of ZSM-5, as we can see. Very strong signal from the center. And this is the magnesium signal. This is a 9.8% magnesium modified sample. We see in the picture, we expect a lot of magnesium from outside, but the interesting thing is nothing goes in. Even though we try very hard to keep everything in the system, they just don't walk in there when you calcine the system. Using the X-ray spectrometer equipped with electron microscope, we can further examine the internal distribution. All the samples shows very uniform and flat distribution of magnesium inside the crystal. And here is the average value of 3 pairs of sample, each pair starting exactly the same material, but one is keeping everything in there, the other is only the ion exchange part. The thing is, the internal distribution is not very sensitive to how much I put it in. And for each pair, the surface coated sample always has more magnesium than the ion exchange sample. But these part, the axis part, presumably is the physical blocking that is not ion exchange with the system. But the interesting thing again here is they are all very low. Even for the most heavily modified sample, this internal magnesium amount accounts for about less than 0.1 weight% in your callus. And in all cases, what I plotted here is the magnesium versus aluminum atomic ratio. Since for the part that is each aluminum, we should associate it with 1 proton to start with, and for divalent exchange between magnesium and aluminum, the maximum exchange in my system should be 0.5. As we can see, for all the samples, even though I try very hard, I didn't remove all the protons by ion exchange, which is good because I don't want to lose active site for the catalytic reaction. All I want to do is physically blocking the pore. So much for the characterization. What I hope to have convinced you is there are 2 things. For the ion exchange modification, surface is clean. I have low and uniform internal magnesium distribution, and I didn't lose all my active site in the form of protons. For the surface coated sample, there are 2 morphologies on the surface. The bulk part you see obviously is a sphere of magnesium 0.1, 0.2 micron in size, but there is a thin film, a few tenths of angstrom is also existing on the surface. The internal loading is quite the same as the ion exchange sample. And always we see a bare open surface that is good for our catalytic reaction, the reactant and product to go in and out. How about the diffusion behavior of our system? This is measured in an electron microbalance, the absorption of toluene under 60 degrees centigrade for a coated sample. The molecules per unit cell of callus is a function of toluene partial pressure for 3 surface coated sample of increasing amount of modification. However, we didn't see any change in the absorption isotherm. This absorption isotherm is indeed linear isotherm under relatively low loading of the absorbent. As we have previously seen in the characterization, not much magnesium is really incorporated in the system. So as we would confirm here, it didn't reduce your absorption capacity significantly, which is consistent, so we can still have those internal openings for molecules to go in and out. But how hard or how fast can they go in? This is dramatically reduced for a loading of the callus, the absorption capacity around 0.3 to 0.5 molecule per unit cell. The diffusivity of toluene isomer as a function of bulk magnesium loading for a surface coated sample is plotted here. With nearly 10% of incorporation of magnesium, we see the drop of diffusion coefficient by over 3 order of magnitude. And if we still remember in the beginning, I have this model. Now I have a small crystal, which is not paraselective, but operated in the low CD modulus region, and it's not paraselective in the high conversions. But if I impregnate it with a certain amount of magnesium, from the previous plot, I know how much diffusion coefficient will be dropped, and therefore I know how much CD modulus I would increase in the system, and theoretically we could predict how much selectivity could we gain by this modification. So the conclusion is, first, the modification, since the internal of the callus was pretty much clean, we didn't lose any absorption capacity, but we do severely retard the diffusional process of the system. And a very interesting conclusion from this one is, what can we learn if next time we want to pick a modifying material to engineer a good system? First, we don't want any ion exchange capacity because that represents a loss of my activity. On the other hand, I wish to, in order to engineer, to control how much coating I can put on the surface, I really like to have something forming a coating rather than agglomerates on the surface. And also, I like to have a controllable modification process like what I use in this system. I can sort of bracket at least how much performance I could get out of a certain initial material to use with. And but what I wish to deliver a message here is in the terms of design, engineering design of a catalyst, we presented here a very simple physical model that you can practically use, and use simple correlations. You can engineer a system to the very accurate degree of, and very practical degree of application. And my time is limited, and I hope I've delivered my message, and thank you very much for your attention to my talk.
Thank you very much, Dr. Mo. This paper is now open to a few questions. Yes.
I'm curious why you chose to use magnesium as the way to produce the coat. There are various ways to produce a coating on zeolite. One of the classical ways is to do silation. And if you do this in a chemical vapor deposition environment, you can do a very controlled coating of the zeolite. Probably better control than you can get by the magnesium deposition.
I agree. In the beginning of this work, we select what material we should use. And if you use solenoid system, you can do probably better modification because the same material as ZSM-5. But how can you differentiate which part is the original ZSM-5 and where you add it up later? This is for a fundamental understanding, and I like to see where they go first and how much I have added to the system. And then later on, I have more confidence about what is the better material to use. I agree with your point. But for the study and understanding of the system, I believe this is the first study of this sort.
Germanium.
It's true. And also, germanium was not really confirmed as an applicable material. And also, I would choose a system that is least studied, of course, and you don't want to somebody scoop up the results before you publish it. And this is one of them.
Last question.
Yes, you showed the data on the diffusivity as a function of the magnesium loading. I presume that was for the coated samples.
Yes.
Do you see any effect on the ion exchange sample?
Minor. I measured it, very minor change. It's consistent, I didn't have time, but it's consistent with our characterization results. Nothing goes in. The reduction was minor. It has some change, but very, very minor, and essentially the same.
Thank you very much, Dr. Mo.